Hello, welcome everyone to the weeks 3 to 4 S2S Webinar Series. My name is Karen Keith and I'm from the National Weather Service Office of Science and Technology. Before we get started with today, I want to let everyone know that we finally have our website set up. I will drop the link to this in the chat after I go through this, but on here we show what we're doing here and also a list of all of our upcoming and previous presenters. And so you missed a webinar, I want to go back and listen to them. We have them all on here. And also you can also, if you're interested in presenting an upcoming webinar, you can click the link here to a Google form, or if you want to subscribe to our notifications, you can click here as well. Like I said, right on the home page, we have our previous people who gave presentations. And if you want to go and look at them, we have their abstracts and their recordings are up on YouTube, so you can watch them. So like I said, I will put this link in the chat. Oh, Maureen did it. Thank you. So it's right there. Please go ahead and take a look at it. And that's where you can get information about the webinar series. Also, for any questions today, we will put this link in the chat as well. Please go to the discussion document and you can chat back and forth with the presenters if you have any questions. If we have time, we can go over a couple of them, but if not, please go ahead on this document to go over any questions, and you can continue on after the allotted hour. So first off, we're going to start with Stefan Tulich on MJO Prediction Skill in Eddy Meridional Mixing of Moisture, Insights from Model with Superparameterized Physics.
All right, thank you. So can everyone see my screen? Hello?
Yes, it looks great.
Okay. So I'm from NOAA Physical Sciences Lab in CU CIRES, and I'd like to start off by acknowledging funding for this work, California Department of Water Resources, and the computing I'll be talking about today is through a CPO allocation. Okay. Trying to get this thing to advance. All right. Not sure why it wasn't working. It's working now. So the ultimate goal of this work is to provide insight for model developers on which aspects of model physics should be looked at, improved, refined for improving MJO prediction simulation in current weather and climate models, and I'm particularly interested in improving the representation, simulation, prediction of the MJO in the NOAA Unified Forecast System. And what I'd really like to try to do today is link what's going on at a process level, or sort of try to provide insight as to how process level parameterizations impact, MJO prediction from a mechanism standpoint. So the outline of the presentation, first I'll talk about the MJO as a moisture mode and sort of review what that means and its implications for basically the mechanism of the MJO that I'm thinking about. Then I'll go into the current state of affairs in MJO prediction and simulation. So where are we at currently? And then I'll discuss an idea about why deficiencies still exist. And then, so there's going to be a fair bit of discussion that leads up to the work that I'm actually doing, which is to use a model with superparameterized physics to test the hypothesis for why we still have problems, and then I'll provide a summary and some future plans. So the MJO as a moisture mode analogy I'd like to sort of think about or illustrate is where you have the donkey and the proverbial carrot out in front of it. And so the MJO is essentially the donkey and the carrot together. And the idea is that the moisture is what causes the convection to move eastward. So the convection of the MJO moves eastward because moisture is to the east and it's sort of being dragged along by the moisture. And so the idea is that interseasonal fluctuations in convection are entirely controlled by moisture through entrainment effects. So wherever moisture goes, convection follows. And the reason the MJO propagates slowly eastward is because its convection does things that causes moisture to move gradually eastward. So this is why I like this analogy, because in this case, the donkey is moving eastward because the carrot's attached to it. And so it's moving eastward to try to chase the carrot, but it's actually causing its own propagation or movement. So although moisture is the focus in the moisture mode paradigm, in practice, what is typically looked at from a diagnostic and theoretical sense is the moist static energy. And moist static energy is the sum of three terms, one relating to temperature, one relating to geopotential energy, and then you have a moisture term. And if you think about the temperature and geopotential terms as being combined, you can think of that as a potential temperature and a moisture energy. And so then what you care about is how the column integrated moist static energy changes with time. And so that's what this bottom equation is conveying. And the changes in the moist static energy column integrated has basically four terms. The first term is a horizontal advection term. The second term is a vertical advection, and then the third and fourth terms are surface fluxes and radiation. So the reason that MSE is useful is because moisture enters the MSE equation. It tends to dominate fluctuations in column integrated MSE because temperature gradients are typically small in the tropics. And then, so you can think of MSE as being a proxy for moisture, but it also tends to be a proxy for convection because convection and moisture are highly correlated with one another on interseasonal timescales. And that's what this figure is sort of illustrating. So this is a composite MJO event, and the contours are the MSE anomalies associated with the MJO as it propagates eastward, and the shading are the rain anomalies associated with the MJO. And you can see that the rain anomalies and the MSE anomalies are almost in phase with one another, showing that if you know what the MSE is doing, then you have a fairly good idea of what the rain field is doing. And so the MSE is dominated by moisture. So this is basically saying that as the MSE moves eastward, the convection follows that are the same as moisture moving eastward. So there have been a number of studies that looked at what controls the horizontal propagation of MSE anomalies. And this is taken from a study by Zhang, 2017. And so we're looking at a picture of the MJO during a certain portion of its life cycle. So the left plots are maps of the MSE over the Indian Ocean when the MJO convection is located there. And so the top panel is the MSE itself, and then the bottom panel is the time rate of change of the MSE. And you can see that you have negative values to the east of the MSE center and positive values, I should say negative values to the west, positive values to the east. So this will tend to make the MSE propagate to the east, and then you can look at the four terms I mentioned earlier and ask which of these terms is contributing to the eastward propagation. And so that's what's shown in the right panel. And so the top panel shows that where you have MSE large values of MSE, there's actually the horizontal advection is causing the MSE to go down there and increase to the east. Whereas, say, the radiation and the surface fluxes are more co-located with the MSE center itself. So those are contributing to amplification of the MSE, but the main term for causing propagation is the horizontal advection. And there's also a contribution from the vertical advection, but the horizontal advection is the dominant player. And so shifting gears to current state of affairs in MJO simulation prediction, this is another paper by Zhang. And what he was looking at is looking at a bunch of climate models and doing an intercomparison of these models and asking which models do better at simulating the MJO and which models do not as well. And he partitioned the models into what were referred to as good and the other being poor. And this is just the left panel is showing a comparison of the good versus poor model in terms of their ability to capture the eastward propagation of the MJO in terms of precipitation. And you can clearly see that this partitioning is distinguishing two types of model behavior. And then the right panel is showing how these models differ in terms of their prediction of, or their treatment of the horizontal advection, or the tendency of MSE. And the main conclusion that he draws is that the primary reason for the differences is related to the horizontal advection of the MSE. So the good models have much stronger horizontal advection of the MSE as compared to the poor models. So this same sort of problem is actually found in the IFS. So we think of the IFS as sort of being the gold standard for MJO prediction from a forecasting sense. So I think their MJO forecast scale far out exceeds essentially all the other operational centers. And in a paper by Jaime Kim in 2017, he showed that while the prediction in the IFS is good, it actually has difficulties in capturing the horizontal advection of the MSE field. And so the left panel is showing the reanalysis where the shading is the horizontal advection term and the contours are the MSE. So you can see the MSE is propagating eastward and you have large positive anomalies out ahead of those MSE anomalies in terms of the advection, and negative anomalies behind. So moistening ahead, you can think of it, and drying behind. But when you look in the actual prediction system, these tendencies, these horizontal advection tendencies are much weaker. And so the MSE signal is much weaker. So why do models have trouble with the horizontal MSE advection? So the study by Jaime Kim, he attributed the problem to basically the prediction of the mean state moisture or MSE field. So this is sort of showing the predicted moisture and MSE field and then the bias relative to the analysis or reanalysis, sort of showing that the model has a pretty substantial dry bias in the MSE field. And so that affects the advection, because the advection is basically, you could think of it to first order as moving around winds of the MJO acting on the mean gradients of the MSE or moisture field. And then in terms of these climate models that Sheng was looking at, a subsequent study sort of showed the same thing in terms of comparing the good versus poor models. They basically differed in terms of their pattern, the mean pattern of the MSE. So the poor models tend to have weaker gradients in the MSE, which then leads to deficiencies in the advection. So this sort of begs the question of what processes control the mean state moisture pattern. And guidance here can be found in a process-based diagnostic study by Sheng et al. And what he showed was that MJOs that do better at simulating the MJO, when you're looking at how rainfall depends on precipitable water, what you find is that the good models tend to have a higher pickup of rain with precipitation as compared to the poor models. So he defined a convective adjustment timescale as a metric, and that's basically just looking at how precipitable water changes with proportion to precipitation. So this is a rate term on the bottom and a moisture, so this is moisture and then moisture over a time. So then you divide that, you get a time scale. And so if you look at the time scale, convective adjustment time scale, he called it, in the good models, it turns to be about a factor of 2 larger than the poor models. So they're basically less effective at removing moisture. So historically speaking, this sort of relationship between precipitation and moisture and the need to represent it has been fairly well appreciated. And so the common interpretation of this sort of behavior or dependence is that convection schemes that do poorly, or models that do poorly, have convection schemes that aren't sufficiently sensitive to moisture. And so the way to address that is to make your convection scheme entrain more strongly so that it is more sensitive to moisture. And so in both the IFS and the UFS subsequently, the entrainment formulation that they've adopted essentially has a strong, an explicit relative humidity term built into it. Sorry, my screen just locked up again. So they have an explicit entrainment effect built in that depends on the relative humidity of the atmosphere. So when the relative humidity becomes very low, then the entrainment goes up. So, and when the relative humidity is near saturation, the entrainment becomes weaker. So this makes the model more strongly sensitive to moisture. And ECMWF attributed their historical gains in MJO Prediction Skill to implementing this sort of entrainment formulation. However, entrainment is not the only possible mechanism for this relationship, for affecting this relationship between precipitation and moisture. And so there's another side to this coin, which has to do with microphysical parameterization and treatment of the efficiency of precipitation production for a given input moisture profile. So if you think about your model physics as receiving temperature and moisture profiles as input over on the left, then the convection scheme sort of choose on these temperature and moisture profiles first, and it has to make choices about how much cloud is detrained to the microphysics scheme on the far right. And then both the convection scheme and the microphysics scheme then have parameter settings that essentially determine how much rain comes out, and then from that rain that comes out of the scheme, how much is evaporated before it reaches the surface. So in addition to entrainment, there's a whole different side, or there's a whole another side of this coin which relates to microphysical processes. And these aspects of schemes, which have not previously been considered in terms of MJO prediction might explain why the IFS and also the UFS, more importantly, still has problems, despite the fact that they are made to strongly, their entrainment is made to strongly depend on moisture. So the basic science question that I'm trying to address is, if you have a model in which you don't have to worry about entrainment parameterization, so physics is treated explicitly, you have no closure assumptions, then how is MSC advection, MJO performance affected by changes in microphysical parameter settings that will effectively control this convective adjustment timescale? And so to do this, I'm using a model with superparameterized physics, which essentially means that I'm embedding a two-dimensional cloud resolving model inside each grid box of a global model and using that as the parameterization scheme, as opposed to a traditional convection scheme. And so the model that I'm using is the superparameterized version of the weather research and forecast model. So this is a model that I developed and described in this paper in James. And while you typically think of the WRF model as being a regional model, and the way I'm using it today is in a global context. So what I'm going to do, or what I'm going to talk about, is a series of MJO hindcasts that I performed, where I've changed the microphysics settings to look at how the model performance depends on changes in microphysical parameters. And so I'm doing a set of 23 large amplitude MJO events. So it's basically focusing on a set of events and then looking at how the simulation or hindcast of these events compares for different microphysical parameter settings. And this left panel shows the composite evolution of the events I'm considering. And then the right panel is showing their evolution in terms of the phase space of an OLR-based MJO index. And so the right panel sort of illustrates the initialization. So in terms of the composite event, I'm initializing essentially when convection is located over Africa. And then I define lag with respect to when the MJO crosses the maritime, right before the MJO crosses the maritime continent. So in this left panel, lag 0 is essentially corresponds to when convection is just west of the maritime continent. And then the forecast runs for 37 days until convection's in the Western Pacific Ocean. And so each of these events, I have a lagged ensemble with 5 members separated by 12-hour start times. The model's initialized with interim data, and the simulations do have daily varying SSTs taken from the interim data, and the motivation is to give the model sort of the best chance for producing a good MJO. And the outer model resolution is 1.4 degrees by 1.4 degrees, so fairly coarse, but the embedded CRMs have 4-kilometer grid spacing with 16 columns. Okay, so the way I alter the microphysics is to change the convective adjustment timescale. There's 2 different ways, at least 2 different ways you can do this that I've explored. And the first is to alter the evaporation efficiency of rainwater. So if you make the evaporation higher, then that tends to reduce your precipitation efficiency. Whereas if you make the value smaller, that tends to increase it. And the other way is to alter the rain accretion of cloud water. So these are 2 different aspects of the explicit microphysics, or the bulk microphysics scheme in the WRF model. And today I'm going to be focusing on the evaporation of rainwater, but I get qualitatively similar results when I alter either of these parameters in the model. So what I'm going to be considering is either a halving or doubling of the evaporation of rainwater. And this is showing how the precipitation depends on column saturation fraction. So this is sort of an RH perspective on the precipitation dependence. And what you see is that when you double the evaporation rate of rainwater, your pickup of precipitation with RH tends to occur later than and more gradually than when you have a halving of the evaporation of rainwater. So this is sort of producing the same sort of behavior as was seen in the good versus bad models, climate model comparison that I talked about earlier. And so you might say, well, these are huge changes in the parameterization efficiency, and the thing to keep in mind is that there's a lot of buffering going on. So when you change these parameters, the atmosphere changes in response, which tends to offset your imposed parameter change. So you're sort of fighting this buffering. So I'm hitting it with a hammer to overcome this buffering. So finally getting to the basic result of this study is when you enhance the evaporation of precipitation, you get a much stronger MJO than when you have the evaporation of water. And that's shown in this comparison. So the left panel is for a doubling of the evaporation. The middle panel is where I've halved it. And then the right panel is the difference. And the shading here is the outgoing long wave radiation. And then the contours are essentially a projection of the OLR onto the EOFs of the MJO to sort of illustrate how the MJO projected fields are changing. And so the difference plot on the right clearly shows that when you make these changes, you get a fairly robust change in the amplitude of the MJO signals. And this is sort of looking at the performance from a phase-based perspective. So the left upper panel is showing that, so the green is essentially, you can think of this as the good model and the red as the bad, and you can see that your amplitude is substantially altered in response to these changes. Interestingly, in terms of skill, you do see that the good model has improved skill throughout the hindcast. However, towards the end of the hindcast, they essentially end up in the same spot. So while there's reduced skill during the middle of the forecast period, by the end they sort of end up at the same spot, and the performance in both cases is, I would argue, quite good. And then if you think about the errors as coming from phase versus amplitude, what I'm finding is that the amplitude errors are the main contributors here. So they both have similar phase, but the main difference is in terms of the amplitude of the disturbance. And then looking at the model performance from an MSC budget perspective, long story short, the main term that's affected in the MSC budget is the advection term, and that's shown down here in the lower left. So the upper left is the MSC tendency together with the anomalies in the OLR and the contours. And if you look at the main contributors to the MSC tendency changes, you find that they're mainly coming from the horizontal advection term. And then thinking about why this advection is changed, what you basically see is what was seen previously that the model where the evaporation rate is doubled has much stronger gradients in the mean precipitable water MSE with respect to the model where the evaporation rate was halved. Okay, so summary and conclusions. The relationship seen in past studies between MJO fidelity, horizontal MSE advection, and the empirical convective adjustment time has basically been captured in a model with explicit physics, where the only thing I changed was the evaporation of rain. So this sort of illustrates that when you're thinking about improving models, the entrainment aspect of the problem is not the only aspect, that there's a whole other side to this problem that needs to be considered in terms of microphysics and the efficiency of your scheme in turning moisture into precipitation. And so the next steps are to perform further analyses to understand this horizontal MSE advection better. So I've alluded to the mean state as being important, but it turns out that the eddy circulations are also important, which was indicated in the title. And that's something I'm currently looking at. And then also looking to perform a similar type of experiment using the NOAA UFS, where we change aspects of the model formulation relating to, say, detrainment of cloud water, evaporation of precipitation, those sorts of things. So thanks. That's it. Take any questions.
Thank you. Actually, because of time right now, if anyone has any questions, please go to the discussion document and you can go and discuss them there. I'm going to move over to the next speaker right now. That's okay. Let's move on to the next speaker, which is Zachary Lawrence, and he'll be talking about a toolbox for verification and validation of stratosphere-troposphere coupling processes in current and future NOAA.
All right, can everybody see my slides?
Yes, look good. Yes.
Let's see here, I'm gonna get all right. I just wanna apologize real quick. I'm unfortunately feeling a little bit under the weather, so I just wanna apologize in advance if I have to kind of clear my throat as I'm talking. But this presentation is primarily going to be a summary of a project we're working on in which we're developing a diagnostic toolbox that can be used for validating and verifying stratosphere-troposphere coupling processes, particularly for future NOAA models. So first, I just want to thank my collaborators, Amy Butler, Judith Perlwitz, Laura Chiasto, and Eric Ray for their help in putting this together. This project is really a collaborative effort amongst folks from CIRES and the University of Colorado, as well as multiple NOAA labs and centers. But before I get into the specifics of what we're doing in this project, I just want to start by giving you a sort of motivating overview about why we're doing what we're doing. Now, I'm sure it's no surprise to anyone here that the stratosphere should be coupled to what happens in the troposphere. But this isn't to say that the stratosphere has no influence whatsoever on the troposphere. In reality, the troposphere and stratosphere are a coupled system such that tropospheric variability forces variability in the stratosphere, and subsequently, stratospheric variability influences variability in the troposphere. Now, this isn't like saying that the stratosphere is going to tell us where it's going to snow tomorrow, but given the highly stratified nature of the stratosphere and the relatively slow timescales on which stratospheric variability occurs, it does have the ability to impact the troposphere on subseasonal to seasonal timescales. So the key players involved in these sorts of troposphere-stratosphere interactions are what you'd expect. They're typically the top drivers or manifestations of variability in the troposphere and stratosphere. So modes like ENSO and the MJO in the troposphere, and the predominant features of the stratosphere, the polar vortices, and the quasi-biennial oscillation. So this coupling between the two layers is primarily mediated by waves and their interaction with the mean flow. So in the troposphere, modes of variability like ENSO and the MJO, these all impact the generation of waves in the troposphere, which go on to propagate upward into the stratosphere and interact with the polar vortices or the QBO and so forth. Now, there's been a lot of research on these kinds of two-way interactions and the impact that they have for predictability on subseasonal to seasonal timescales. So I'm going to briefly cover some of that, but I'm going to focus mostly on findings that have more to do with the influence that the stratosphere can have on the troposphere. So first, the stratospheric polar vortices. You've probably seen schematics like these that I've shown here in the upper left that discuss associations between the strength of the polar vortex and the jet streams and how these relationships can particularly impact winter weather. So the basic association is that a strong and stable polar vortex tends to be linked with a stronger and more polar jet stream, which helps to keep cold air locked into the polar region, while a weaker and wavier polar vortex is linked with a weaker and wavier jet stream that more often allows cold air to dip south. And so these links are generally characterized via what's known as the annular modes. And so in the stratosphere, these annular modes basically characterize the strength of the polar vortices, but in the troposphere, they approximately characterize the strength and position of the mid-latitude jets. So variations in the strength of the polar vortex are driven by upward propagating waves. So in cases where you have stronger or weaker than normal wave driving, the vortex can become anomalously weak or strong. And these weak and strong vortex events typically have long time scales. So when you look at composites of the annular modes with respect to these events, you find that you can get long-term coupling between the stratosphere and troposphere such that annular mode anomalies of the same sign as those in the stratosphere are more common in the troposphere for weeks to months following these vortex events. And that's what this plot I'm showing on the right shows. It's comparing northern annular mode composites lagged with respect to weak vortex events in this top panel and strong vortex events in the bottom. And you can see how anomalies of the same sign preferentially occur in the troposphere for around 60 days following these events. Now, further research has found that essentially when subseasonal forecast models are initialized during these anomalous vortex states, tropospheric predictability beyond roughly 2 weeks tends to be better, particularly for indices like the annular modes or the North Atlantic Oscillation and so forth. And that's what this figure shows on the left. This is from a 2020 paper that showed with a particular S2S model, predictive skill for the NAO increased when the model was initialized during weak or strong vortex states, particularly in the weeks 4 to 6 range. However, there's been other recent work that has shown that subseasonal models can struggle with predicting vortex variability. And so this plot on the right shows the lead time dependence for models to capture various kinds of vortex events in their ensembles, including strong vortex events and weak vortex events. So for one thing, this figure kind of shows that models often struggle to predict appreciable risk for vortex events in the 2 to 3 weeks range. And it also shows that there's a strong sensitivity to how well models represent the stratosphere. Basically, models that have a lower model top typically do a worse job at predicting these events, even at the shorter lead times. So there's some sensitivity here to how well resolved the stratosphere is in these kinds of models. Now switching to focus on the stratospheric QBO, studies based on observations and reanalysis have shown that there are several pathways through which the QBO can affect the troposphere, particularly on subseasonal to seasonal timescales. So this schematic on the left is from a 2018 paper by Leslie Gray in ACP. And in that paper, the authors review and analyze these different pathways. One of the pathways that has been identified to be particularly important is related to the QBO-associated impacts to temperatures in the lowermost stratosphere. So essentially, the QBO leads to temperature anomalies in the lower stratosphere that are consistent with the QBO wind shear because of thermal wind balance. And these temperature anomalies can impact the upper troposphere by influencing the height of the tropopause and the stability of the upper troposphere. And obviously, both of these things can impact things like tropical convection. So, one example of this that has been the subject of a lot of recent research is the observed relationship between the QBO and the MJO. So this figure on the left is from a 2017 paper, and it shows in the colors the lead lag correlations of outgoing long wave radiation anomalies with those centered around the maritime continent, but separated into composites for easterly QBO versus westerly. So essentially, the figure shows that during easterly QBO phases, the MJO is generally more vigorous and exhibits, greater amplitudes and more consistent progression through different MJO phases. Now, this is just one figure, and there's been other studies that have shown further evidence for this relationship. But notably, studies that have focused more on whether this relationship exists in climate or forecast models, these have come up with mixed results. Most of the time, models don't really catch a robust relationship between the QBO and MJO. One example of this I'm showing here on the right is from a 2019 paper in which the authors show that the skill of many S2S models in predicting the MJO is not statistically significantly different for different phases of the QBO. Now, this figure I'm showing specifically highlights one case, and it shows how one model struggles essentially to maintain the vertical structure of the QBO temperature anomalies in the lowermost stratosphere. And so, something like this is thought to have a negative impact on the ability of models to skillfully forecast or represent the MJO. So these two examples related to the polar vortices and the QBO kind of bring up the issue of model deficiencies and biases in the stratosphere. So here I'm showing how distributions of stratospheric zonal mean winds representative of the Arctic polar vortex, how these change as a function of lead time for two different subseasonal models. And these are real results. I'm just not specifying which models these are, but you could see the distinctly different biases. The top model quickly drifts towards a model climate with a too strong polar vortex, while the bottom model more gradually drifts toward having a weak vortex. So just from looking at these, you might expect that without some sort of post-processing or bias correction, the top model would likely always underestimate the risk of weak vortex events and overestimate the risk for strong vortex events. But more than that, because these coupling processes between the troposphere and stratosphere are dominated by wave mean flow interactions, there's significant potential for these things to feed back on one another in ways that can negatively impact the potential for aiding subseasonal predictability. So for example, the propagation of waves horizontally and vertically is determined by the mean flow. So if you have a polar vortex that's biased too strong, its interaction with a wave pulse will be impacted by that bias in the zonal mean flow in ways that simple bias corrections can't necessarily account for. There's also multiple timescales at play. For example, if your QBO temperature anomalies decay too quickly in week 2, then you can't necessarily expect any sort of QBO MJO or QBO convection mechanism to have a very strong bearing for prediction out, weeks 3, weeks 4, and so forth. So this is a significant problem. Model biases in the stratosphere can lead to model deficiencies in representing these coupling processes between the two layers, and that can negatively impact their potential as sources of subseasonal predictability. But if we think a bit more optimistically, we have a particularly good understanding of the radiative and dynamical controls that drive the stratospheric circulation and thermodynamics. For example, global mean stratospheric temperatures are under strong radiative control. So if a model has a global mean temperature bias in the stratosphere, then usually that means the bias is a result of something related to radiative transfer, like the distributions of ozone in the stratosphere. But overall, this means that the stratospheric biases in models can tell us a lot about their sources, which means that just by figuring out what the biases are, we can generally determine where to look to address and ultimately reduce them. So in other words, there's strong motivations for evaluating the representation of the stratosphere and strat-trope coupling processes, both from the standpoint of prediction, but also from the standpoint of model improvement. And so that finally brings me to the specifics of our project, which is titled A Diagnostic Toolbox for the Verification and Validation of Subseasonal Stratosphere-Troposphere Coupling Processes in NOAA's Unified Forecast System. This is a project funded by the NWS Office of Science and Technology Integration under their Weeks 3-4 program. And our team of investigators and researchers is led by Eric Ray from CIRES and the University of Colorado. But as I mentioned before in the beginning, we have strong ties with NOAA labs and centers, including CSL, PSL, CPC, and we also have collaborators from EMC and NCAR working with us. And so there's 3 primary goals of our project, and these are to, 1, develop a diagnostic toolbox that can be used to assess stratospheric forecast biases and stratospheric-troposphere coupling processes and incorporate this into MET+. 2, formulate new validation and verification metrics designed to exploit opportunistic stratospheric information for improving Weeks 3-4 prediction. And 3, apply these diagnostics and verification metrics to NOAA GEFS reforecasts and real-time forecasts in collaboration with NCEP CPC. So the toolbox, which forms the basis of our project, is intended to fulfill primarily 2 purposes. One is to diagnose those lead time dependent forecast biases in the stratospheric circulation, stratospheric variability, and in strat-trop coupling. And this is to help directly answer what are a model stratosphere related biases, where do they occur, and how do they impact predictability. The other purpose is to provide sort of target metrics for measuring the coupling between the stratosphere and troposphere and any links to the coupled atmosphere-ocean system. And this is to help specifically answer, when is this stratospheric and strat-trop coupling information useful for purposes of prediction. Now, one of our major deliverables will be to apply this toolbox to the recently released GEFS v12 hindcast dataset and real-time forecasts. In reality, we're using GEFS v12 as a platform to develop this toolbox. But importantly, the results we get from GEFS v12 are going to serve as the baseline from which the progress of future NOAA models can be assessed. And this is particularly important because one of our ultimate goals and final deliverables is to incorporate our toolbox into MET+. So if you're not familiar, MET+ is a verification framework that's developed by the Developmental Testbed Center, and it's going to be a component of NOAA's UFS. And so essentially as a component of UFS, MET+ is going to be a singular unified framework from which developers and end users will be able to evaluate any and all aspects of the UFS. And so this sort of underpins why we want to both apply this toolbox to GEFS v12 and incorporate the toolbox into MET+, because by doing so, we'll be providing developers and end users with both the information and the tools necessary to be able to consider the stratosphere and strat-trop coupling in future updates and implementations of the UFS. So we're still relatively early into this project, and we're still working on fully fleshing out the toolbox, but I have some preliminary results that I can show you that are based on the set of GEFS v12 hindcasts that are now publicly available. So what we're looking at here are the zonal mean biases in zonal mean, zonal winds in the top rows and temperatures in the bottom for week 1 in the left columns and week 5 in the right columns. And these results are composited in DJF and JJA. So these biases are calculated with respect to the ERA5 reanalysis over the full 2000 to 2019 hindcast set. So one of the things you can see is that there are some apparent biases already in week 1, particularly in the middle to upper stratosphere above 10 hectopascals. These are primarily due to differences in the initializations that are likely just due to the simple differences in reanalysis. GEFS v12 was initialized using its own reanalysis data set that's inherently different from ERA5. So these biases are likely just due to that fact, and especially since they're mostly in the upper stratosphere, that tends to be where these kinds of differences have the largest effect. But if we look at the week 5 columns, what we see is that there's an apparent winter pole cold bias for both hemispheres. And so the high latitudes, this results in too strong of zonal mean zonal winds in the polar vortex region. But basically, overall, what you notice is that there's a global bias in temperatures. And so that tells us that this specific, the global mean temperature bias is likely something radiatively driven, whereas the biases that are more latitudinally dependent, things that might affect the vortex, are likely to be dynamically driven due to either resolved or unresolved wave drag. Now here we're still looking at zonal mean biases, but this time I'm focusing only on the tropics and only up to 10 hectopascals because I've composited these based on the phase of the QBO at 50 hectopascals. So in the colors we have the biases in the zonal mean zonal winds, while on the line contours we have the biases in temperatures. So the top row is for westerly QBO, while the bottom is for easterly. And essentially what we see is that generally the QBO winds above 100 hectopascals have a tendency to relax towards weaker westerlies. This is really apparent in this westerly composite with this blue region where the QBO winds should be westerly. So these negative values indicate weakening of the westerlies. But this is also consistent at other levels. And during the easterly QBO phase where instead we have this positive bias in this region, this means that the easterlies are instead relaxing towards 0 meters per second. Now, in terms of temperatures, we can still see the imprint of the global mean warm bias. In both cases, the temperatures increase in going from week 1 to week 5. And you can see this just by looking at the placement of the 1 Kelvin contour. In both cases, at week 1, it sits just below 30 hectopascals, whereas in week 5, it has descended to around 50 to 70 hectopascals. But there's still some slight differences between these composites. We can see that the warm bias specifically extends further down into the lowermost stratosphere in this easterly composite. And this is important because the easterly phase of the QBO is when we expect to have cold QBO anomalies in this region. And so that's when we expect this to have, the greatest impact on things like the MJO and convection. Now, we haven't just been utilizing the GUESS V12, we've also been looking a bit at CFS V2, which has been used for subseasonal to seasonal forecasts for many years now. The main difference between these systems is that there aren't as many stratospheric levels with the CFS V2 data available to work with. So generally, we've put together comparisons between GUESS V12 and CFS V2 as histograms. So here we're continuing to look at the QBO by examining the distributions of tropical zonal winds at 50 millibars, with the two different systems in the colored lines and ERA 5 in the background is gray. So you can clearly see the bimodal distribution in this case that representing the different phases of the QBO. But in particular, we could see that compared to CFS V2, GUESS V12 appears to start with better initial conditions because this easterly peak with CFS2 appears to be shifted to the right with respect to the reanalysis. But you can also see that both of these systems at week 5, these bimodal peaks have shifted closer together. So this is indicating, again, the relaxation of winds towards 0 meters per second. So this kind of points to there being likely a common mechanism at play here, something potentially related to parameterized wave drag that allows the winds to relax similarly. Now here we've gone back to looking at the extratropical stratosphere. These histograms are for the 10 hectopascal zonal mean winds at 60 degrees north, composited during the extended winter season of DJFM. So these are essentially representative of the strength of the polar vortex. In this case, we can see both models are initialized consistently, showing a close match to the histograms for ERA 5. But at week 5, we see that these systems diverge. As we saw before in the zonal mean plots, the GUESS V12 shifts toward having a too strong polar vortex, and particularly overestimates the occurrence of strong vortex extremes. In contrast, CFS V2 tends to shift in the opposite direction toward a vortex that is too weak. Now, as a final comparison here, we're looking at distributions at 100 millibars for a diagnostic known as Eddy heat flux. And Eddy heat fluxes in the stratosphere essentially provide a simple measure for the amount of vertical wave activity. So in a simple sense, it measures wave driving in the stratosphere that would generally lead to changes in the strength of the polar vortex. Now in this case, I've divided the distributions into heat fluxes decomposed for zonal wave numbers 1 and 2. And this is because only the largest planetary scale waves are able to effectively propagate into the stratosphere. So we have wave number 1 in the top row and wave number 2 in the bottom row. But basically what we see is that both models maintain the general structure of the heat flux distributions at week 5. And importantly, they're both capable of generating heat flux extremes, and that's important for driving strong and weak polar vortex events. So that's a good thing. But the primary difference we can see between these two systems is that for GES V12, the wave 1 heat fluxes drift towards being slightly high. And this isn't necessarily a large bias, but it's more apparent in GES V12, especially when you look at the actual statistics of these distributions. So this basically means that for GES V12, wave driving of the stratosphere tends to be partitioned slightly more often into wave 1 than wave 2. So these figures that I've shown basically give the overview of the results that we have now, but we're still in the process of fleshing out the toolbox. And so while the results tell us quite a bit about the GES V12 stratospheric biases, they can only really provide us with some expectations about how these biases may impact strat-trope coupling processes and predictability. So for example, the biases in vortex strength shown in GES V12, that makes us wonder whether there could be any impact on the life cycle of these kinds of vortex events. Maybe because of the strong bias, weak vortex events are not persistent enough in GES V12 to show that they appreciably impact the troposphere. Similarly, with the QBO biases that we saw, we wonder, how the temperature biases in different phases may have an impact on things like a potential QBO and MJO connection. So in thinking ahead, these are the things that we're thinking about as we continue to flesh out our toolbox. Now, one of the last things I wanted to mention is that since we've been using GES V12 as a platform to develop our toolbox, we've put together a special subsetted version of the GES V12 data. So if you've worked at all with the publicly available GES V12 hindcast data set, then you'll know it's kind of difficult to deal with. The data is publicly available in the Amazon cloud, which is great, but it's stored as GRIB, and the files are chunked in ways that can be kind of a pain to deal with. The other problem is that since we're specifically interested in strat-trope coupling, it's also a ton of data for us to wrangle, since we need several fields and basically all the pressure levels that we can get to be able to examine how these strat-trope interactions look. So essentially what we've done is we put together a zonal mean data set of the 35-day GES V12 hindcasts as netcdf files. So I put a screenshot over here that shows what's contained in these files, but it's mostly just things like zonal winds, geopotential heights, temperatures, and things like that. So if you use Python and X-ray, these files are really simple to work with and do simple data analysis and make quick and easy plots like I'm showing here. But basically, we're planning to make this data set publicly available. The total volume of it only amounts to about 1.4 terabytes, so it's not too large. But the main thing is at the moment, we're not sure of the exact timeline. So if you're interested in this data set and you'd like to know when we make it available, you can get in touch with me at my email address here, and I'll be sure to give you updates about this data set and when it's released. So that's really the end of my talk. So just to conclude, we've been using the publicly available GES V12 hindcast data set to develop a toolbox to examine stratospheric biases and strat-trope coupling processes in NOAA forecast models. We've applied a limited set of these diagnostics to GES V12, and that's provided us some insight into potential implications for strat-trope coupling in GES V12 and provided us with details on the range of stratospheric biases that are present. And I also just discussed how we've put together a zonal mean data set of the GES hindcast, and that's something we're working to make publicly available. In terms of where we're headed, first we'll primarily be fleshing out the rest of the toolbox, and we'll be fleshing it out with diagnostics that will sort of help us to better understand the nature of these biases that we've seen and their implications for strat-trope coupling. And from there, we'll be doing a bit more of a formal skill assessment using the data we have. And in parallel with that, we'll be working with our partners at EMC and NCAR to integrate our toolbox into MET+, and also work with partners at CPC to demonstrate the utility of some of these diagnostics for real-time monitoring and forecasts. So I'll stop there, and I'd be happy to take any questions or hear any feedback that you have. Thanks.
Thank you. We are at the top of the hour, so we should let people go. But if anyone has any questions for either of our speakers, please go to the discussion document and ask them there, and you can chat back and forth there. Appreciate everyone coming today and hope to see you all in March at our next webinar. Thank you.